Welcome to today's paper reading. Today's paper is titled, Self-Play Fine-Tuning Converts Weak Language Models to Strong Language Models. This paper, published in the Proceedings of the 41st International Conference on Machine Learning, presents a novel fine-tuning method by Zixiang Chen and colleagues from the University of California, Los Angeles. This paper explores the potential of advancing large language models, LLMs, through supervised fine-tuning, SFT, using human-annotated data. The authors propose a new method called self-play fine-tuning, SPIN, which allows a strong LLM to be developed from a weaker one without additional human-annotated data. SPIN employs a self-play mechanism where the LLM refines its capabilities by generating its own training data from previous iterations. The method is theoretically proven to achieve the global optimum when the LLM policy aligns with the target data distribution. Empirical evaluations on benchmark datasets show that SPIN significantly improves LLM performance and even outperforms models trained with direct preference optimization supplemented with GPT-4 data. Large language models, LLMs, have shown remarkable capabilities in various domains requiring complex reasoning and specialized knowledge, such as mathematical problem-solving, code generation, and text creation. These models are typically aligned with desirable behaviors through methods like supervised fine-tuning, SFT, and reinforcement learning from human feedback, RLHF, which rely heavily on human-annotated data. This paper introduces a novel fine-tuning method called self-play fine-tuning, SPIN, inspired by self-play mechanisms in games like AlphaGo Zero. SPIN allows a weak LLM to improve itself without additional human-annotated data, by having the model play against itself. This approach eliminates the need for expert annotators and converges the model's distribution to the target data distribution, demonstrating significant improvements in model performance. In the field of multi-agent reinforcement learning, self-play has been notably effective. A key example is AlphaGo Zero, which significantly outperformed human players using self-play. Subsequent research has further explored this method, leading to various adaptations. Our work is the first to apply this self-play approach to large language models, LLMs. Regarding synthetic data for LLMs, supervised fine-tuning has shown remarkable effectiveness with human-crafted data, particularly in tasks like code generation and mathematical reasoning. However, the cost of acquiring such data is high, leading to the increased use of synthetic data. Advanced LLMs, such as the GPT series, are often used to generate this synthetic data. Unlike previous studies, our approach directly generates synthetic data from the target model itself, aiming to enhance the performance of LLMs through self-play fine-tuning. The large language model, LLM, is parameterized by theta and generates a response Y from a given prompt X. This process is autoregressive, meaning it leverages previously generated tokens, forming a Markov process. Supervised fine-tuning, SFT, is used to adapt the LLM to specific tasks by minimizing the negative log likelihood loss, which aligns the model's predictive distribution with high-quality responses. Reinforcement learning, RL, fine-tuning, on the other hand, aims to maximize a reward function R, X, Y, while including a callback labeler, KL, regularization to prevent excessive deviation from a reference model. This method requires a preference dataset, often compiled through human or AI feedback. The method introduced in this section is called self-play fine-tuning, SPIN. It involves a two-player game where the main player's goal is to differentiate between responses generated by the language model and those by humans, while the opponent aims to produce responses indistinguishable from human responses. The core of SPIN is the self-play mechanism, where both players are the same language model from different iterations. In each iteration, the main player is trained using the integral probability metric, IPM, to maximize the difference between the target data distribution and the opponent's distribution. The opponent is then updated with a callback labeler, KL, regularization term to prevent excessive deviation and stabilize the self-play. This method contrasts with direct preference optimization, DPO, which operates in a single iteration and requires a preference dataset. SPIN, on the other hand, is iterative and can use various convex and decreasing loss functions, making it more flexible. Figure 1 illustrates the differences in model generation between iteration 0 and iteration 1 compared to the ground truth completion. In iteration 0, the model's response is fluent but includes specific percentages that may not be accurate, potentially indicating hallucinations. By iteration 1, the model's response shifts to a qualitative summary without specific percentages, aligning more closely with the ground truth and adding more detailed information. In this theoretical analysis, we examine algorithm 1 under specific assumptions. First, we assume the loss function, t, is monotonically decreasing and convex, which is true for many common machine learning loss functions. Based on these assumptions, Theorem 5.2 establishes that the global optimum is achieved if and only if the parameter theta t aligns the model's data distribution with the target data distribution. Specifically, if the model's distribution matches the target, theta t is the global minimum. Conversely, if they do not match, theta t is not the global minimum. Theorem 5.4 further explores the logistic loss function, showing how updates to the opponent player's distribution are controlled by the factor 1/lambda, influencing the stability of the training process as the model's distribution approaches the target. The empirical analysis of spin highlights significant improvements in model performance across various benchmarks. Spin effectively breaks the limitations of supervised fine-tuning, SFT, and achieves performance comparable to direct preference optimization, DPO, at the initial iteration without additional human-annotated data. The experiment setup involves using the Zephyr 7b SFT full model, derived from the pre-trained Mistral 7b, and fine-tuning it on the UltraChat 200K dataset. Synthetic responses are generated from 50K randomly sampled prompts. The evaluation is conducted using the Hugging Face Open LLM leaderboard, which includes 6 datasets assessing different capabilities of large language models. Detailed evaluation settings are provided in Appendix B. Figure 2 illustrates the average scores of the self-play fine-tuning, SPIN, method at different iterations on the Hugging Face Open LLM leaderboard datasets. The performance of the base model Zephyr 7b SFT full, which has been fine-tuned on the same dataset used to generate synthetic data, is also reported for comparison. This figure effectively demonstrates the enhancement in benchmark performance achieved by SPIN across various iterations. The SPIN method introduced in this paper uses a self-play mechanism to iteratively fine-tune a weak language model into a strong one. This process involves the model self-evaluating and enhancing its performance without needing additional human data or feedback from stronger models. Empirical results show that SPIN significantly improves language model performance across various benchmarks, even surpassing models trained with additional human data. Looking ahead, the authors suggest exploring dynamic target data distributions and reducing the volume of required synthetic data as promising avenues for further enhancing language model capabilities, potentially reaching superhuman levels. Figure 3 presents a performance comparison between the self-play iterative network, SPIN, and direct preference optimization, DPO, training across 6 benchmark datasets. At iteration 0, SPIN achieves performance comparable to DPO, which uses 62,000 new data points. By iteration 1, SPIN surpasses DPO on the majority of these datasets, demonstrating the effectiveness of the self-play mechanism. The datasets include the ARC challenge, truthful QA, and an average performance metric, highlighting the broad applicability and success of SPIN over DPO. Figure 4 illustrates the training dynamics of the Zephyr 7b SFT full model on 50K synthetic data across multiple epochs during iteration 0. The figure highlights that the most significant improvements occur within the first 2 epochs, with only modest gains thereafter. This suggests that while extending training duration maintains performance, it does not surpass the results achieved in iteration 1, emphasizing the importance of iterative training. Thank you for watching.